Have you ever wondered how a machine learns to play a game? Not by reading a strategy guide, but just by playing. It tries things, messes up, gets some points for a good move, and slowly, somehow, it gets smarter. Well, that's the whole magic behind reinforcement learning. Today, we're going to unpack the fundamental rulebook that these machines use to learn how to think. Let's get into it. So, here's our game plan. First, we'll look at the two big ways these learning agents can approach a problem. Then, we'll pull up a map of all the common algorithms so you can see how they're related. After that, we are diving deep into the absolute core of RL, the official rules of the game. We'll take that rulebook apart, piece by piece, understand its one crucial, kind of weird property, and by the end, you'll have a rock-solid foundation for how this whole thing works. All right, so to make sense of this huge field, it really helps to start by asking two simple but really powerful questions about how any of these learning agents work. And the answers to these questions create the first major fork in the road for how we design them. Okay, the first big question is this. Does the agent have the game's instruction manual? A model-based agent, on the left, totally does. It has an internal model of its world, which lets it predict what's going to happen next if it makes a certain move. But a model-free agent? It has no manual at all. It's just dropped into the game and has to learn everything from pure trial and error. It tries something, sees what happens, and slowly builds up an understanding of the rules as it goes. The second question is all about the agent's strategy. How does it actually decide what to do? Well, a value-based agent is kind of like a calculated player. It's obsessed with judging the value of every situation. It's always asking, how good is this spot I'm in? And then it just picks the move that leads to the highest scoring future spot. A policy-based agent, on the other hand, is much more direct. It doesn't really care about scoring spots. It just learns a policy, which is basically a cheat sheet that says, when you see this, do that. It's the difference between carefully weighing all your options versus just following a direct order. So we've got these two major dividing lines, right? Model-based versus model-free, and value-based versus policy-based. Now let's see how these categories lay out a map of the entire RL algorithm world. Okay, I know this flowchart looks a little intimidating at first, but it's really just a family tree based on the two questions we just asked. See that first big split at the top? On the left, you've got your model-based crew. But honestly, most of the action these days is on the right, in the model-free world. And that branch splits again into the two strategies we just talked about. You've got value-based methods down one path, with famous names like Q-learning and DQN. That's the one that taught itself to master old Atari games. And on the other path, you have the policy-based methods, which you see a lot in things like robotics. This map really helps you see how everything fits together. Now that we have the lay of the land, it's time to get to the absolute heart of it all. We need to understand the formal rulebook that defines the game world for any learning agent. And this has a name. It's called the Markov Decision Process, or MDP for short. So, what on earth is an MDP? Well, think of it as the universal language for describing any reinforcement learning problem you can imagine. It's a formal, mathematical way to describe any situation where an agent has to make choices, and the results are a mix of what the agent controls and just plain old randomness. Honestly, understanding the MDP is understanding the bedrock of all modern reinforcement learning. And this diagram right here shows the core dynamic perfectly. The agent and the environment are locked in this constant feedback loop. It's a cycle. At every single step, the agent looks at its current state, it takes an action, and the environment immediately responds by giving back two things: a reward or a penalty, and a new state to look at. This loop, state, action, reward, new state, over and over again, is how all learning happens in an MDP. Okay, so we know an MDP is the official rulebook. Now let's actually open that book and look at the pieces and the rules inside. You can think of it like learning what all the different pieces on a chessboard are and how each one is allowed to move. Turns out, every single MDP is built from 5 core things. First, you've got states. These are just all the possible situations the agent could ever find itself in, like every possible arrangement of pieces on a chessboard. Second, actions. These are all the legal moves the agent can make from a given state. Simple enough. Third, transition probabilities. Okay, this one sounds a bit technical, but it's basically the physics of the world. It answers the question, if I'm in this state and I take this action, what's the chance I'll end up in some other state? Fourth, we have rewards. These are the points. This is what tells the agent if it's doing a good job or a bad job. And finally, you have the policy. This is the agent's brain, its strategy, that tells it what action to pick when it's in any given state. Let's make this super concrete. Just look at this diagram. The green circles, S0, S1, and S2, those are our states. The orange circles, A0 and A1, those are the actions the agent can choose from. Now, see the numbers on the arrows? Those are the transition probabilities. So, for example, if you're in state S0 and you choose action A1, there's a 70% chance you'll just land right back in S0. And finally, you can see the rewards, like getting a sweet +5 points for making a certain move. This little diagram is a complete, self-contained universe, all defined by the rules of its MDP. Now, there is one absolutely crucial fundamental assumption that makes all of this math actually work. It's a special property that simplifies everything, and it's called the Markov property. So this Markov property is a really powerful idea. It basically says that the future is independent of the past, as long as you know the present. To put it another way, to predict what's going to happen next, all you need to know is your current state and the action you're about to take. The entire long history of how you got to this exact moment, the system says, it's completely irrelevant. To put it even more simply, think about a game of chess. To decide on your best next move, all you need is the current layout of the board. You don't need a video replay of the last 30 moves that led to this position. The current state contains every single piece of information you need to make the best possible choice. That's the memoryless property in action. What matters is now. So let's take a quick breath and recap. We have just put together the essential toolkit. These are the foundational concepts you absolutely need to understand pretty much any conversation about reinforcement learning. So here are the 4 biggest takeaways. First, we can sort almost any RL algorithm by asking 2 simple questions. Does it use a model of the world? And does it learn based on value or based on a direct policy? Second, the Markov Decision Process, the MDP, is the universal blueprint we use to frame these problems. Third, every single MDP is defined by just 5 things: its states, actions, transition rules, rewards, and a policy. And finally, that all-important Markov property, which assumes that only the present moment matters for deciding the future. So we've laid out the entire game board, we've defined all the rules with the MDP, we completely understand the world our agent is living in. But, that brings us to the biggest question of all, doesn't it? How does an agent actually learn to play well? Knowing the rules is one thing, but how does it figure out the optimal strategy to get the most points possible? Well, that is the next amazing step on the journey into reinforcement learning.